Good morning, everyone, and welcome to today's HNRCA seminar. Thank you all for joining us. There is a well-known saying that a picture is worth 1,000 words. I thought of that expression when preparing today's introduction because our speaker has truly mastered the art of communicating complex science through figures, networks, and visual representations that allow us to see food in a completely different way. So it is a great pleasure to introduce Dr. Giulia Menichetti from the Channing Division of Network Medicine at Brigham and Women's Hospital and Harvard Medical School. Dr. Menichetti is a statistical and computational physicist specializing in network science. She leads the Foodome project, and that's what she will be talking about, an ambitious effort to track the complete chemical complexity of the foods we consume and to develop quantitative tools that reveal how these food-derived chemicals may influence human health. Her lab develops AI-powered approaches to predict the bioactivity of food small molecules and to design more reproducible food quality metrics and public health interventions. What makes her work so exciting for us is that it brings together several areas that are central to the mission of the HNRCA: nutrition, aging, precision nutrition, food systems, artificial intelligence, and health. Her work challenges us to move beyond traditional dietary categories and to think about food as a complex biological and chemical system. Today, she will speak, as you can see on the screen, on the Foodome project, Emerging Patterns in Food Data Science. Giulia, thank you very much for joining us. We are delighted to have you, and we look forward to your presentation. And I will now turn it over to you.
Well, thank you so much, Joseph, for this wonderful introduction, for really giving you, a bird's eye view of what I've been trying to achieve. So I'm honored to be here. And just to add to this fantastic introduction, I want to just stress again, I'm a physicist by training, despite now I'm an assistant professor in medicine. This is very interesting. And, before leading this group, I studied basically, as you heard, statistical and computational physics. But most importantly, I have specialized in network science. So what is network science? Is the science that by studying how the elements of a system interact is able to predict the emergent properties of, and let's say overall behavior of that system. It's also important for this talk, is also important to define emergent properties. Well, these are the properties that cannot be explained by looking at the features of the single elements building the system. And let's keep this in mind when we discuss how to classify foods or even dietary patterns by focusing sometimes only on single nutrients or ingredients, right? So we want to have a different approach to these type of tasks. So most importantly, I do not work on the Foodome project alone. These are all the junior researchers working with me. Our team spans computer science, chemistry, medicine, and epidemiology. And I want to stress that this diversity is not optional. Somehow it reflects the structure of the problem itself. So when we started the Foodome project, as physicists expert in complex systems, we were inspired by the Genome Project to look into the building bricks of human nutrition and their interactions. So we look into food molecules. We had experience in drug discovery, for example. And particularly, of course, we look into food small molecules. So given our initial expertise in a field that is called network medicine, we had expectation for food molecules very similar to drugs. That is, extensive records describing their presence in food with quantified amounts and interaction with known protein targets, both human and maybe even microbial. Well, we soon realized that this scenario was extremely far from reality, so we were a little bit delusional. And we collected our initial insights into a perspective piece where we define as the dark matter of nutrition all the chemicals present in foods and largely invisible to epidemiological studies and standard food composition databases, such as national food composition databases. This piece was published in 2019 in the first issue of Nature Food, And at that time, in open source databases, we found approximately 26,000 compounds sparsely distributed across different foods. And through the years, by combining a variety of machine learning tools from, let's say, text mining in scientific literature to genomic predictions, and even metabolomics experiments, we reach 139,000. Actually, now we have more than 140,000 chemical compounds, and we keep growing as right now, as I was saying, basically, we are ingesting another big chunk of data, so the next estimation is going to be even bigger. You can read the story about, let's say, these past years of research and our different attempts to map the dark matter of nutrition in this annual review that you see here in the corner. But let me give you some examples. So the 69 nutrients documented under the umbrella of the USDA. So there are several different databases in the USDA. For raw garlic include important things, such as, for example, vitamins, ascorbic acid, or vitamin C, and non-essential amino acids such as alanine, right? Yet the database does not track, well, important organosulfur compounds such as allicin and adenine, which are key drivers of the cardioprotective and antimicrobial effects of garlic, or the polyphenol that you see here, picoumeric acid, which is protective against carcinogenesis and inflammation. So these are just three bioactives of the more than 6,000 small molecules we documented in raw garlic, many of which are secondary or specialized metabolites acting as the plant's chemical defense against stressors such as predators or extreme weather conditions. So let's take a closer look to this library. We like to call this library NDM, so Nutritional Dark Matter. So our NDM library. I would say that by now, hopefully, everyone knows OpenAI, Claude, Gemini, et cetera, et cetera. Probably you're integrating this pipelines into your daily work. Well, at the core of the transformer architecture that has revolutionized natural language processing, we find the attention mechanism. So this mechanism allows models to focus on specific parts of the input data when making predictions, basically very similar to how humans pay attention to certain aspects of a scene while ignoring others. Part of this process leads to context-aware representations of concepts, words, and sentences as dense vectors that we like to call embeddings. And you will see these embeddings coming up multiple times in this talk, even later when we discuss food processing. And these embeddings, with very, very broad strokes, can inform downstream tasks. So language models and large language models started with human language, so we mentioned natural language processing, and have now moved to the language of biology and chemistry. So, for instance, chemical language models such as Malformer, trained by IBM, work on the canonical smiles representing a molecule and represent basically each food molecule that you see here as a vector embedded in a high-dimensional space, 768 dimensions in this case. And this allows us to basically visualize the structural and functional similarities of food molecules in our NDM library. So, as I was mentioning, the points here are color-coded, represent food molecules, and they're color-coded according to their subclass with at least 500 compounds. And on the right here, you see where all chemicals tracked for garlic sit, and in particular, the three bioactives that I mentioned before. This is a pre-trained model, and we will see later application of fine-tuning of this specific language model for specific tasks. So rather than behaving as the standard macro and micronutrients that serve as energy sources, providing, for example, essential amino acids for growth and repair, or regulating enzyme activity by acting as cofactors of co-substrates, many of the molecules in the NDM may be closer to drugs. And we investigated this hypothesis, of course, and here, well, you can see it right away. I added basically the drug molecules found in drug bank to this initial map. And around 20% of the molecules in drug banks, so pharmaceutical drugs, appear also in the NDM, implying that basically these molecules are found potentially in the ingredients that we consume. And this is just 101 exact structural matching. I'm not even doing similarities, right? Because of course we expect somehow that this molecule could be identified for pharmaceutical purposes. To give an example, rosmarinic acid that you see here, right? That is a polyphenol known as an antiplatelet agent, sits relatively close to a synthetic antiplatelet agent that is called clopidogrel. We see that basically the drug compounds tend to cluster in a distinct region of the NDM, you see here, which is predominantly hydrophilic, and which is also expected considering the most common drug design principles. I think it's very interesting that virtually no area of this drug-related space is untouched by food molecules, represented in gray and orange here, okay? Reflecting the extent to which many current drugs, of course, have been inspired by naturally occurring compounds, and also suggesting a vast untapped potential within the broader chemical landscape of food. So, of course, there are not just similarities with drugs, there are also differences. So in contrast to drugs, food molecules never encounter our cellular networks in isolation, but they do so in conjunction with other food molecules that are often interdependent. So we show this interdependency here in panel A, so this one here, where we cluster the Spearman correlation matrix of the chemical concentration or amounts, in this case, amounts is actually more correct, measure in 108 raw fruits and vegetables, whose amounts basically in multiple foods were measured, were cataloged by the USDA. So we observe distinct clear clusters, right, of highly correlated compounds, often reflecting shared pathways in the plant metabolism. We can give examples, of course, of this idea. So vitamin K1 and lutein, while having at least one order of magnitude difference in their average concentration, show a very strong correlation. So we are in this part of the plot due to their shared biosynthetic pathway and common precursor. In contrast, if we look for delphinidine, that is here, that is an anthocyanidine, well, it belongs to a separate cluster indicating no shared biosynthetic pathway. So this finding suggests that many food molecules produced together by an organism metabolism share structural and functional similarity. And subsequently, they often target the same areas of the human interactome. What is the interactome? When I talk about human interactome, you will hear this multiple times, is the map or network of all the human proteins interacting with each other. So it's basically our favorite model of our cellular systems. Another example I think is very relevant here of what I've just discussed is provided again by anthocyanidins and anthocyanins, which differ only by the attachment of sugar molecules. Their presence in food shows a very strong Spearman correlation, as we have seen here, right? And they also modulate a common neighborhood of the interactome, as you see in panel B, okay? And this happens through the action of 10 shared protein targets. So something about what we're currently doing right now, well, we're currently studying the structural and functional redundancy typical of food molecules. This implies that there are several structures that are often produced together by the metabolism. Of course, in this case, we're talking mainly about plant metabolism, and have similar function and similar targets, but fluctuates at different orders of magnitude. So deterministically, they have a similar function and trigger the same areas of the interactome, which, and this is a very interesting and important point, in drug combination is often seen as a bad thing. But because this problem is rather stochastic, this redundancy, this interchangeability somehow allows for the emergence of a modulated effect from the noise. So again, this is one of the main differences with drugs and drug combinations. So beyond structural similarity that we have studied basically with large language models, so using Maltformer, we can bring more biological networks into the picture to study function with more comprehensive tools. So one of my, as I said, one of our favorite cellular network is the human interactome or protein-protein interaction network. Here, as you can see in the picture, each node is a protein and each link is a physical interaction between these proteins. So think about this as information passing through different neighborhoods of a map, where proteins basically that are involved in similar biological mechanism coexist, tend to live together in the same neighborhood. I can give you further examples of this. So, well, we can work with a, let's say, well-known molecule, sulforaphane in this case. It is quite interesting because while this compound is very well researched in the literature, it's usually not documented in national food composition databases. And so for sulforaphane, I retrieved 58 experimental targets. We have created harmonization tools that do so comprehensively and systematically for all the molecules we have in the NDM library. And these targets create in the interactome a subgraph. So the network proximity, so you have to think about a way to quantify distances on this map somehow. So we call this proximity. So the network proximity of sulforaphane's targets to other proteins, but in very interesting proteins linked to known disease phenotypes or endophenotypes, allow us to quantify the likelihood of sulforaphane modulating inflammation, more or less in the same neighborhood of the subgraph of sulforaphane, coronary artery disease, again, very much in overlap. Think about comorbidities and common and shared mechanisms of actions, and epigenetic modifier in a slightly different part of this neighborhood. So last year, we developed 2 optimized Python libraries to annotate with targets, large libraries of compounds, and run comprehensive network medicine analysis. Everything I've shown you so far is what we call network medicine analysis. These networks can be personalized through metadata on the nodes, so on the proteins in this case, and on the edges, so on the interaction between proteins, falling in the more general framework of graph neural networks. I'm not ending this part on epigenetic modifiers by chance, since they are the focus of one of the major projects in my lab, as they are, at least according to me, an important mechanism of action for food molecules, often mentioned but poorly characterized at scale. In the coming months, we will share this work where, leveraging network science, we expand on the hallmarks of epigenetics and fingerprint all molecules present in the NDM, proceeding to predict the epigenetic properties of food ingredients and world cuisines. And comparing basically this molecular analysis with epidemiological analysis on healthy aging. So please stay tuned. I can't wait to bring this to public audience. So to apply network medicine, as you've seen so far, we needed to annotate the targets of the NDM library by aggregating and harmonizing 9 databases. We did the same exercise for drug bank, and you already see this in basically the representation of molecules in drug bank with Maltformer. And so, but because these are drugs, or we already knew some targets, but thanks to this exercise that we did some months ago, we found basically all the lost target information not disclosed publicly. And so statistically speaking, we saw that the annotated food compounds show similar statistics compared to drugs, both in terms of number of annotated targets and strength of the interaction. Here, the strength of the interaction is measured by P. Campbell. Of course, by design, we expect drugs to be enriched in the upper end of P. Campbell. So here you have the strongest binders. Yet there is a drastic issue for food molecules compared to drugs. And let me click. Naturally occurring compounds and additives are generally poorly annotated compared to drugs, limiting our ability to apply network medicine, so the study of bioactivity, right away. Only, as you can read here, 6% of our NDM library has at least one known binding annotation with human targets. So we have a problem, and we needed to predict targets to have a more complete assessment of the target profile of our food molecules. This brought us to develop AI models to predict the binding between food molecules and proteins, unfortunately revealing many of the biases of current AI models and their lack of generalizability. Indeed, you have to think about food molecules as minorities, and AI models are really not good as figuring out minorities. So, very, very long story, incredibly short, because really today we don't have the time. Here I'm showing two articles which are the results of stressing the state-of-the-art AI models in drug discovery to predict binding interaction for food small molecules. We realized that these models were not really learning what they were supposed to learn, and consequently, they didn't understand ligand protein binding from first principles. Therefore, they were unable to generalize to poorly annotated molecules, such as those in food. So I would say that without this tough test on food small molecules, this research wouldn't be here. And a key take-home message is that high performance in trivial tests, as often reported in CS literature, could be achieved for the wrong reasons. And AI literature is affected by this type of shortcut learning because unfortunately there is a strong focus on performance and not interpretability. What is shortcut learning? Well, shortcut learning in a nutshell is, let's say your model learns you are training your model to identify cows, right? And you will have plenty of picture of cows, in a very nice and green landscape, meadows and stuff like that. And then you go to a new task and you want to identify a cow on a beach, okay? Or in a parking lot. Well, the model will fail. And why? Because it focused on a completely different piece of information compared to what you wanted. It focused on the landscape, basically, rather than learning to identify cows. And this happens in biochemistry as well, and in drug discovery. So these results have inspired many new projects and models. I like to see this as part of the wealth of discoveries that transformative data resources have beyond their initial purposes. So we have to work as a field on generating more transformative data sources for nutrition. So we have recently received a grant from the American Heart Association on a project called Food Inspired Cardiovascular Therapeutics. And an idea here is that while the mapping of the NDM will go on for the next years to come, we can start capitalizing on the richness of the chemical library that we built to find molecules for drug discovery. As we've seen before, while many drugs have been inspired by naturally occurring compounds, this generation process can become more and more systematic now that we have bigger and bigger repositories of naturally occurring compounds. Beyond what you see here that relates to cardiovascular diseases, think about cellular senescence, hallmarks of aging, and even molecules hitting GLP-1 pathways. The idea here that I think it's important to stress is that mapping the chemical composition of food at high resolution not only will help empower precision nutrition, but could be beneficial for successful partnership, for example, with the industry. So from a computational standpoint, the idea here is to build AI models good enough and fast enough to allow large-scale screening of the NDM library against basically the whole interactome. So we're talking about 18,000 proteins, human proteins. We could also do this with microbial proteins, of course. Then more computational expensive models such as molecular dynamics, autodocking, AlphaFold, and many other models can come later on a prioritized list. In this case, we have fine-tuned. So what you see here, the beautiful fish. is nothing more than the fine-tuning of the language model mole former to predict a proxy of the binding strength between the NDM molecules and a therapeutic targets of interest. Here, for example, I extracted basically the fine-tuned embeddings, so not the general embeddings as we have seen before, and I color them according to their distance from a selected therapeutic target. So here, the closer you are, so the smaller is your shortest path distance, the higher, the stronger is going to be your the better is going to be your binding affinity. And so therefore, this is somehow a way to identify a region, a set of molecules that somehow we want to pursue with experimental, by doing experiments, right? So indeed, we are testing this part here, this part that you see in green, in vitro, and the results are very promising. So let's pause for a second. Up to now, I have discussed only results on the biochemical characterization of food molecules and their bioactivity. But this is just an angle. The reality is that data science of food connects several layers, at least 4, that we should address to generate meaningful impact and understand which models, which architecture are currently feasible. I have summarized here 4 major groups. The first one, food composition scatter a little bit everywhere with different resolutions. Let me give an example of this. For example, different selection of nutrients, different data types. For example, when we look at the ingredient list versus the nutrition facts. So it's always very important to compare, to be aware that real foods in grocery stores are quite different from the foods that we use in epidemiological studies. So real foods in grocery stores have nutrition facts and ingredient lists. And while model foods in epidemiological studies, well, they are foods that represent averages of multiple real foods, usually reporting nutritional composition with more nutrients compared to the nutrition facts. The second tier or layer that you see here is food classification, key to understand the food behavioral aspects, so dietary patterns, organized knowledge, and to communicate scientific findings through public health and dietary guidelines. The third bucket that you see here is what I like to call the macro level cohorts to run epidemiological studies. And the fourth bucket here is the micro level, molecular databases to add potential mechanistic explanation. So acting on the modern food systems requires an extensive body of knowledge, data collection, and multimodal computer science approaches. We have also to acknowledge the influence and the interdependence of each layer. For example, much of what I have shown you up to now connects layer 1 and layer 4. Unfortunately, current data availability in all layers is still limited, and this is a remarkable difference compared to all the omics contributed to precision medicine. So our journey towards food processing is an example of connecting different layers of the food systems. Indeed, at the beginning of our journey, we ask ourselves a very simple questions in a very bad English. How much nutrients is in food? Do we have a model for it? And you have to forgive me, I am a physicist, right? So we like to think about models everywhere we go. So we started by collecting the nutritional profile of all foods in the American food supply. So again, we went back to the USDA. And here, for example, you see the nutritional profile of raw onion as reported, again, in the USDA, but where we change a little bit how the data was reported, right? So concentration per 100 grams, so we converted everything in grams per 100 grams, cover 8 orders of magnitude, and we like to think about this range as a range driven by the complexity of biochemical processes responsible for nutrient production and modulation. And again, just a clarification, when I say nutrients here, I refer to all the chemicals and broad chemical classes reported in the food composition database. So don't read too much into what I call nutrients. So we proceeded in studying basically how each single nutrient is distributed across the food supply, as plotted here for vitamin B12, thiamine, zinc, gadolinic acid, and total protein. Total protein is actually a control that should partially diverge from the others. So the probability Q that you see here captured the food source variability for a single nutrient. Yet we haven't found any guidance on its expected functional form. It's going to be log normal, it's going to be a gamma distribution. What is it going to be? So despite noise and batch effects, because for sure the US food supply is not a random sample of food, so of course this is relevant for statisticians, we saw, I would say, a common pattern emerging that you can see here as well. Long story, very, very short. Each nutrient seems to be characterized by a similar functional form in the log space, only translated at different average levels of concentrations. We find that log normals with similar logarithmic standard deviation, so fold change, basically, seem to best describe the observed distribution, allowing us to scale all nutrients and compare them on a single plot, as I've done here. This is what physicists like to call universality. The same chemical laws with different parameters generate chemical concentration with a statistical behavior which is consistent upon rescaling. Moreover, we have also observed a cleaner behavior for simple ingredients like fruits and vegetables, and we have also recently confirmed the results in metabolomics experiments on plants, and you can see these results in bioRxiv. So while we could indulge here in discussing, I would say, evolution for a very long time, there are more practical applications, and the observed common scale of fluctuations in the log space, followed by all nutrients, suggests a methodology to detect outliers. The patterns of different nutrient outliers is then informative of type and extent of processing, as we can appreciate here with different versions of onions and transformations. This implies that we have found a natural metric of processing or transformations beyond the simple presence of additives, right? And a very important message here that I want to stress is that it is important to look at these patterns in a holistic fashion, not one nutrient at a time. So we basically, some years ago, with this formalism, we stumbled upon food processing. And we had no clue about the epidemiological discussion on this topic. So just to bring everyone at the same level, so food processing is known to alter the concentration of native nutrients. Processing usually comes from the addition of extra salt, sugar, fats, and other additives whose purpose is to mimic the sensory qualities of fresh or raw foods or mask undesirable sensory attributes of the final product. Why am I mentioning here highly processed food or ultra processed food? Well, because experts have not converged yet on a single definition grounded in clear, measurable data science or clinical outcomes. In this presentation, I will use the terms interchangeably, but be aware that different nomenclature correspond to significantly different philosophies on the topic. So NOVA is undoubtedly the most famous classification system. It introduced the concept of ultra-processed food. It was an important paradigm shift. It is used in more than 95% of the current epidemiological studies, so it's extremely popular right now. We have 4 classes. Here I'm not showing a very small class, class 2, that covers culinary ingredients like table sugars, oils, fats, and salt. And while this classification framework is very popular, no one can deny this, it's still qualitative and descriptive. This has created issues of portability since each data set comes with different data available to match the description. The classification task is still also predominantly manual. All these aspects have brought to documented issues of poor inter-rater reliability and lack of reproducibility. And just to give you a number, just from 2009 to 2017, the definitions have changed 8 times. So despite the limitation of our current tools that are there, we cannot deny it, there is a growing body of literature connecting food processing and human health. So here I'm listing some of the most interesting and plausible mechanisms. We have hyperpalatable food defined by addiction scientists. It describes a food with high levels of at least 2 nutrients among fat, salt, and sugar. This combination would not be normally found in natural foods. So somehow it recalls what we have seen with the plots that we have seen before, but for all nutrients, not for just 3 nutrients, right? So this sensory characteristic related to high levels of 2 of nutrients out of the 3 that I just mentioned are believed to override satiety signals, promoting excess intake, and even though I would say the exact reward-related neural pathways remain an area of ongoing discussion. So I just don't want to jump right away into addiction, and it's still, I think it's something that we're still figuring out. This focus draws attention to the nutritional quality of UPFs, which is notably not a formal criterion within the NOVA classification system. So again, there are different groups fighting on these topics. Hyperpalatability, however, is not simply a function of elevated levels of fat, sugar, and salt. Hyperpalatability also involves physical transformation to food that often alter the nature of food matrix. So then we have to move and discuss what is the food matrix. So let's first introduce the food matrix related to the discussion of highly processed food. So changes in the food matrix characteristic of ultra-processed food may negatively affect nutrient bioavailability, postprandial glycemic responses, and satiety. So if we want to give a definition of a food matrix, well, we could say that it represents the complex physical and chemical organization of nutrients and bioactive compounds mainly in whole foods. So we take whole foods as a reference. And it plays, as we said, a crucial role in digestion, absorption, and satiety. So researchers have found that UPFs would frequently show textures that promote rapid consumption, such as crunchiness or softness, also low chew resistance, and melt in the mouth consistency. So the structural changes in the food matrix often correlate with inclusion of industrial additives that further modulate how UPFs interact with our body. And of course, then we have to go and look into the relevance of non-nutritive sweeteners, emulsifiers, and their connection with the microbiome and inflammation, and also in general how artificial sweeteners and emulsifiers have been connected to, for example, increased risk of cardiovascular diseases. So if food processing systematically and reproducibly alters the nutrient profile of food, we can train a classifier to predict NOVA classes. And this is exactly what we did using tree-based models like Random Forest and XGBoost that are ideal for tabular data as nutrient table. So in 2019, we had very limited training data provided by Montero's group on NANE's FNDDS 2009-2010. The performance were very good without any sophisticated tricks. This proved our goal. That was basically to show that the nutritional profile as a whole is predictive of the degree of processing. For each food, the classifier delivers 4 probabilities showing how certain the model is in making that decision. And you can see it here. Furthermore, we can provide standard deviation since we can use several different models trained on slightly different information. So the performance of the classifier were extremely good. As I said, no sophisticated trick, but most importantly, stable when we progressively remove nutrients, right? Up to the panel that is covered by the nutrition facts. This is very important because it allows us in our subsequent paper to bring a classification system designed for model foods in epidemiological studies, right? So the data types were extremely different and mainly nutrient-based, no ingredient list in model foods, to real foods in grocery stores where there was no manual classification available at that time. And so therefore to bridge an important gap. We learned something very important while building the classifier. This is what I like to call the brain of the classifier, that is represented by a PCA of the probability simplex, meaning that each food is represented by a vector of probabilities, and we reduce the dimensionality to 2D. You can see that the classifier works well in this cross-validation setting, because basically all manually classified foods are close to a specific corner, so they segregate well, right? And we can follow the trajectory of onion again, right? Yet a unique manual label was assigned to only 34.25% of foods in FNDDS, so in the US food supply. Everything else was not classified because not consumed or needed to be decomposed, meaning that there is still no unique label. There is no unique 1, 2, 3, and 4 associated with foods like that. You can still calculate, of course, the overall caloric intake from NOVA4, but you need to go through the decomposition of a food in its list of ingredients, which is very specific to how FNDDS is built and is definitely not comparable to, for example, ingredient list brand food products, and definitely does not generalize well to other population studies. So you can always extend the prediction beyond cross-validation, basically, to the remaining part of FNDDS, finding that basically the space now is filled. This suggests that while the classifier can make a decision, it is not as confident as before. And from this exercise, of course, you can always come up with a percentage describing the food supply, right? So you can do the standard CS task, right? So we predicted that 73.35% of the food supplies is ultra processed, a number that was confirmed by other independent publications, some with manual assessments, some with algorithms. But while this number got picked up by a lot of people and by the media, of course, this was not the take-home message. This result, and again, see how the space is filled, shows that basically the incredible nutrient variability within each NOVA class and the struggle to assign to each food a specific NOVA class, forcing incredibly different foods in the same category. Here we made the decision to move to a gradient assessment that we call FPRO, because while NOVA classification has limitation, it still provides information on industrial processing, and combined with the nutrient, it can still inform a ranking system, which is likely more stable and less prone to errors than a black and white classification. FPRO, our score, so focus on this line here, is calculated as the projection in the probability simplex on the line that goes from pure NOVA1 to pure NOVA4, and mathematically reduces to a very simple and elegant formula that you can see here. So this is how the rank projection of the whole FNDDS looks like. Unlike traditional nutrient focus assessment, very important this, by the way, FPRO does not evaluate individual nutrients in isolation. The same nutrient change will determine a shift in FPRO according to the values of all the other nutrients. Basically, FPRO is a non-linear function of the nutrient profile. It's not that easy to cheat with FPRO, let's say, if you're reformulating things. The score is, of course, in good agreement with NOVA, as you can see here on the right, by following the colors. So unprocessed, processed, and ultra-processed. However, nutrient concentration gives us more granularity, allowing us to discriminate between products otherwise considered identical. So this would be the 70% of the food supply. This, of course, resonated deeply with epidemiologists that found basically differential disease risk for subgroups of UPFs in large population studies in the following years. Why having a continuous score is important? Because we can study the variability characterizing different food categories and suggest alternatives within the same group without drastically changing the dietary pattern of an individual. For example, you could be a breakfast cereal person and variate your choice of cereals, but you rarely, if ever, consume eggs. So this type of dietary modeling led to the What We Eat in America classes, groups of foods with similar nutrient content and usage. Here I'm showing, for example, these classes ranked by median processing score. And here there is an example for breakfast cereals where we observe an increasing pattern of F-Pro determined by several nutrients alteration like the decrease of fiber content, sugar addition, fat addition, and vitamin and mineral fortification. These cereals are considered equally ultra-processed by NOVA. F-Pro also, and this is very important for connecting the different layers of the food system, allow us to systematically derive personalized dietary scores weighted by calories or grams and run them against more than 400 different phenotypes coming from NAs, among which, for example, you find metrics relevant to biological aging. So we basically perform what we call an EWAS, an exposome-wide association study. Very similar to the philosophy, like to what happens in genomics. So once done this, we had all we needed for an in silico substitution study where we quantify the population health prediction when changing basically just one or few items, so very small nudges. For example, switching cereal types, but still keep consuming cereals. So by 2020, let me see how much time I have. Okay. By 2020, we understood we had very flexible models trained on the nutrition facts, and then the pandemic kicked. Many people started buying their groceries online. So I distinctly remember the moment when I was like, okay, we should really understand how these models perform on real foods, not just model foods. We should run this into the wild. So building on the idea of minimal substitution that I just mentioned to you, we mined the website of 3 major grocery stores, collecting more than 50,000 products with nutrition facts, ingredient lists, prices, and calculated their F-Pro and other trends such as price per calorie versus degree of food processing. And it's very important to stratify per category because these trends are category dependent. Given the flexibility of the algorithm, we also score other databases such as the USDA branded food products and compare it with our real-time data collection. Remember, at this point, we had only credible manual labels for model foods, so foods without the ingredient list. So the website that you see here, grocerydb.net, is now, so we actually move it from the original platform to this new website that is called grocerydb.net. And the website has been going through a major makeover. One of the features I really wanted to allow to visualize, basically I really wanted to include somehow, is to give the possibility to visualize the processing score from multiple models trained on different information and architectures, so that we can quantify agreement and people can choose their favorite model, right? A bit like you choose a model on ChatGPT. Last but not least, this website will always be free as part of my efforts to push for open science and data transparency in nutrition. If you see initiatives that sound like it, but are behind a paywall, feel free to reach out to me if that's not me, okay? So from 2019, many things have changed. Our friends at Open Food Facts, a French nonprofit organization with a big team of volunteers, systematically scanned foods in grocery stores and generated a crowdsourced database with progressively better metadata. On foods, they try to assign NOVA classes following different rules. While this is not perfect and open to daily discussion and evolution, as a data scientist, I appreciate their work since it's a great resource connecting Nova to real food in grocery stores. Therefore, this increases basically our training, the number of data types, and therefore the number of models and architectures we can test. What do I mean when I talk about data types? So let's give an example here. So LLMs are ideal to take as input mixed data types, such as product name, ingredient list, and nutrient panel. How can we do this? Well, we can create a sentence about the product. As you can see, basically this opens the possibility to input data with missing information or missing data types and study the stability of their vector representation or embedding. So those vectors that I mentioned at the beginning. This sentence is the input to a language model such as BERT or other language models. And pay attention because this is basically similar. I'm almost done, Jose. I'm seeing you. Pay attention because basically this is similar to how you could query ChatGPT about ANOVA classification. And these models are not great at paying attention to numbers. And you can quantify this by perturbing the embeddings changing nutritional values and keeping everything else the same. So if you want to stress the let's say quantitative side of this representation, this is actually not the best way to do it, and you shouldn't query ChatGPT with that. By the way, then we can play with our original models, the Food Pro X models, using the nutritional panel. Here, in particular, we focus on 11 nutrients, removing nutrients with high missingness, and complement then also with the number of additives. So these models work with tabular data, for which missingness could be a problem. And this is, of course, was not an issue in FNDDS because everything is reported, but it's definitely an issue in real world data where you need assumption. And finally, we tested some rules of thumb, such as classifying according to their number of additives or the length of their ingredient list. This is mainly for interpretability to avoid always relying on complex models. And I will jump to, I would say, my last slides. We study, so feel free to read this chapter. It is basically a playground of different models that you can perform to try to figure out what it means to predict food processing. And if we stick to the classification problem, so we look into NOVA classes, we can assess basically performances, right? So we call them AUP and AUC for the sake of conciseness. This is an imbalance problem, so the area under the precision recall curve, so this part here is the most appropriate metric. What do we learn? The bulk of nutritional data is very predictive. Indeed, let's look at the Food Pro X models that you see here, right here. The number of additives gives a little extra when we are predicting things. BERT, so the language models, improves on the already good performance of Food Pro X everywhere, mainly NOVA 2 and 3, where the text captured in the ingredients seem to be discriminatory. Yet the complexity and resources needed to choose the hyperparameters and possibly fine-tuning are significantly different. This is, of course, a baseline for LLMs that could be further improved with fine-tuning, and the explanatory models leveraging length of the ingredients, so this stuff here, right? And number of additives are very good predictors of what is NOVA 4 and what is not. This should be a warning for policymakers. We are now beyond NOVA. We do not really have the time to discuss this unless there are questions about it. We are currently trying to solve the issue of predicting a history behind a product. And so this will inform basically experiments and clinical trial to precisely figure out what went wrong with our food supply and maybe find an intelligent way of processing food, right? Not everything is bad. And let me just jump to the conclusions. So this was an overview of what we are currently working on in the lab. I would like to finish today with a couple take-home messages. You have seen how much we can do when data is open source. nutrition will get in its rightful place in precision medicine only when it generates data sources comparable to those that have already transformed fields like genomics and transcriptomics. It's important to integrate models in the way we reason, in the way we think. Models are our friends. When we start thinking about a classification system, for example, we should ask ourselves right away what types of data we have and what types of model we can implement to support our classification framework. Models can do many things, from understanding pros and cons of annotation systems to standardized inputs and enhanced reproducibility, up to allowing for sensitivity analysis and uncertainty estimation. Last but not least, the real question is how to build data ecosystems that create value for both the industry and public health. Today, why am I jumping and trying to work with what I have? Because today, a lot of high resolution information about food composition and processing do exist, but it's fragmented, proprietary, and not standardized. So this fragmentation limits not only our research and the reliability of our models, but also the ability of companies themselves to position their products accurately in a data-driven market. If we move toward a structured, interoperable, and partially shared data frameworks, companies gain as well. More precise and fair evaluation of their products, better tools for reformulation and innovation, increased transparency. And this is particularly is becoming a competitive advantage, especially with younger consumers that are used to vet their product. They are digital native, okay? So the goal is not full data disclosure, but selective, standardized, and incentive-aligned data sharing and governance. So in this sense, data generation I think, goes beyond the scientific challenge. It is a governance opportunity for transforming our food systems. And I am done. Thank you so much.
Thank you. Thank you very much, Giulia, for a fascinating and very stimulating presentation. I think we still have some unfinished business, right? Well, now let's go to the questions. And let me read it to you. From Larissa, fascinating talk. In your models, do you account for bioavailability and for variability of concentrations of components in foods?
We can do that. We don't always do it because, as you probably know, this information is not available. So for those cases in which we have this type of information, well, in terms of bioavailability, the same models applies to the metabolites, right? So this means that you don't have to work right away with the chemical compounds that you have. So you can work right away with the chemical compounds you have in food, but we can predict the metabolites. So a similar network approach can take into account really if the chemical compound has been metabolized or not, and therefore have a very precise understanding of the cellular effect because the metabolite is actually detectable, okay? So that's one way of doing this. Concentration-wise, yes, it's basically if available, and of course, again, we have to come up with an assessment at the cellular level. You could basically threshold and somehow renormalize the impact on the targets, right? So the link between these chemical compounds and the targets, so the binding affinities, are, you could say, we can estimate an effect, therefore the strength of that link, okay? So according to the availability of that compound, then the effect of the drug or the compound on specific phenotypes can be basically rescored. Hopefully I answer all the questions.
Okay, thank you. The next question is from Sai Das. This is amazing work. Thank you for sharing. For your studies on population consumption and health stats, macro, what database sample size do you typically think is optimal for the network analysis?
Oh, that's a great question. So when we do the network analysis, well, that's okay. I'm going to be very, very honest with you. So population studies and network analysis right now are two layers of the food system that are currently not very well connected, meaning that you see, to personalize my network, I can use omics. This is, for example, much of the work we have been doing at the Channing Division of Network Medicine, working with not just the interactomes, but also gene regulatory networks and other types of networks, and make them very personalized, okay? The issue is that not necessarily you then have dietary information to match the same population data, okay? And one of the very good things that are happening, I would say, at the Channing Division of Network Medicine is that currently in our multi-omics cohort, we have been collecting untargeted metabolomics, and part of my work that I've not presented today is leveraging untargeted metabolomics data and artificial intelligence to somehow come up with a sense of your dietary patterns, looking directly to the small molecules we can detect in your fluids. So I cannot give you a number. What I can tell you is that right now, unfortunately, matching networks and diet is still a problem because of the lack of data on diet.
Thank you. I will skip the accolades because we don't have too much time, but let's go to the next one. Shandong one. We know that food components and drugs differ significantly in their dose-response relationships, primarily in potency, specificity, and predictability. Food components often follow a flatter U-shape or linear dose-response curve. I was wondering regarding your food component-inspired therapeutic or drug discovery, if we could get some wrong information by using AI or foodomics to link chemicals to specific biological and interactive pathways and diseases without considering those information.
Wow, so this is a very, I would say that I agree. I can explain you better what we have been doing, okay? What AI does, so what the AI currently is doing is not learning, so the calibration curve is not done by AI. What the AI is learning is basically, it goes back to experimental studies where binding affinities have been measured, okay, and learns. So these are many times are in vivo studies, basically. And what it does is to, in vivo or in vitro, sorry, I don't want to say something not precise. And it does basically, it learns to predict a graded version of binding affinity. Okay, so when you have a target of interest and then a small molecule arrives, I can tell you more or less if this is a strong binder or not. Okay, we try to increase the resolution of basically this task. Then it is fundamental to do exactly what you have done and to test what you have done on a prioritized list in experiments. Okay, so we're not doing what you're describing with the AI part, but we need to go into the experiments on a prioritized list.
Thank you. We don't have time for one final question, but I will do it anyway.
I'm not running anyway. I'm available.
Yeah. That's from Nagla. I was wondering if you have stratified your analysis of foods coming from different geographic regions of origin to see if there is the same range variation in the compound profile or if they are present in different concentrations.
Okay, so I can tell you more or less what we tested for. So the different types of stratifications. So, and by the way, when you read my papers, please go into the SI. These are basically PhD theses. So there is much of it, there are a lot of interesting work that many of these questions are in the SI. So for the universal laws, what we have done was to first look into other national food composition databases for which we had quantities, right? And just to see that more or less the shape was matched and that log normal was selected as the best performing function. Beyond that, we use the sample variability of the USDA. The USDA in the standard database provides you in the what was called the standard reference, used to provide an average, but then the USDA has expanded to also provide with Food Data Central also the single samples, and so you can include variability into this analysis. Finally, we did stratifications, meaning that we look into mainly food groups, okay? And for me, at least at that time, we looked specifically in what are the plant groups versus like plant-derived foods versus non-plant-derived foods. And what is interesting is that you can see actually the math supports this. You can see that the shape of the log normal slightly changes, and this is just a matter of standard deviation. It's still a log normal when you look into secondary / specialized metabolites compared to primary metabolites. And why? Because basically there is a compounded noise that the math that I derived in the SI somehow supports, and that clearly comes up when you look into different food groups, specifically plant-based. We didn't really look into other food groups around the world beyond looking into the overall sample of national food composition databases.
Well, Giulia, we are really grateful that you joined us today and share your work with us.
Well, thank you for inviting me.
Your presentation gave us a powerful example of how we can we should see food and its relation to health in a really new way. Thank you again.
Well, thank you so much for having me. Please feel free to reach out to me because I could have gone on forever. So okay. Probably you saw that. Okay. Bye-bye. Have a great day. Bye. Bye-bye.